Like we could record it, throw it on the channel if y'all want to look at it again or something. We say something interesting. Yeah. So go ahead and start with things. So like we all know and love the good old attention architecture, or it all basically is the attention. Computer is the attention mechanism. So that's like A is equal to our queries times our transpose keys over like the square root of D. It's like dk. So you take the softmax of this and multiply by the values, and this is your attention mechanism. So I'm going to simplify it by just having qk transpose and v. So it's just these three. So the shapes of this are, I'm going to remove the heads because the heads are kind of like, it's basically just a part of this. It's not important for the discussion because it's basically like you throw it in the batch dimension, so it's not useful. So basically this is S by D, this is D by S, and this is S by D. And your quadratic complexity comes from here. So this is your S by S matrix. Right. So that's your quadratic in memory and time right here. So yeah, I guess I could talk about Big Bird first because that kind of was the first thing. I want to see exactly, actually Longformer. I want to see the diagram real quick. So like there's sparse attention, which I want to talk about, and I want to talk about why that's stupid. And then there is linear attention, which is, I think, a better approach.
Is that yours?
Yeah, it's mine. So you have like so this here basically forms your attention matrix.
QQT, right? Sorry,
QK transpose. So you have your queries here along the rows, and you have your keys along the columns.
Yeah.
So like this. So this would represent like, and then we want it to be causal as well. There, these are all zeros. Yeah, that works. So yeah, we're going to be talking about causal attention, though sometimes this works for bidirectional. Some formulations of the linear attention. So what you do with like sparse attention is you're like, well, what if I just take a subset of this? So what if I just take like the diagonal? So I just take like, say, a diagonal of size 3 or something, and what that does is if this is our output, say this is our third output here, right here, then this output is composed of the first 3 inputs. But then if I have the fourth output, that's composed of the 3 inputs before it. So it basically assigns a locality to it, and it's basically a convolution.
It's like window attention?
Yeah, this is window attention.
Oh.
So
That's
if
Longformer, right?
Yeah, Longformer, Big Bird.
Longformer?
I think, yeah, Longformer uses this. They have like this, and then they add some other things. They're like, oh, what if we have random attention? Like, what if we have something here and something here, but we don't compute this part here? And at a point, you're like, like, what are we doing here? Like, like what is this? So I guess I could go through all things they do. So they basically have sliding window attention, where they basically say we have a window of size 3 or something like that. And that basically says the output token is going to be composed of the last window size number of tokens. So that could be like 512 or something. It's not a good idea. Because like if I have information here, like this token just can't be composed of that. So they try to get around that by like adding dilations and stuff, but it's just a convolution at this point. Like it's literally just a convolutional neural network. Like if you have sliding window attention, that's a convolutional neural network, where the convolution is whatever this size is. So you either have a convolution if you have sparse attention, or you have a full graph, which is full attention. So because this convolution is basically saying, give me the last 3 elements. So it's a convolution over a sequence. So like it's not a new idea. They're like, oh, what if we add global? So what if all tokens can attend to this one? But it's like, that's stupid. So sparse attention, I think, is really, really dumb. Don't do sparse attention. Like, the only time you would use it is if you're like, I want to do sliding window attention. Like, I have a sequence length of 16 million, and I want to do a sliding window of like 1 million or something like that, then it's like, all right, that's sure, that's reasonable, I guess.
Is that really all sparse attention is?
Yeah, it's just how do you select parts of your attention matrix in a way that seems smart, but it isn't. So
You
it's
can only like kind of access the attention for that specific windows, right?
yeah. What?
Like you, but like you can only like how the model runs. It's going to just look at the attention to each window, right?
Yeah. Like if I have, let's say I have a window of size 3.
Yeah.
So that would be this here. What is this? 1, 2, 3, 4. So output 5 would be composed. So O5 is going to be composed of value 5. So
Yeah.
itself, value 4, and value 3.
Right.
But that means if I have any information here, it's not in that.
Yeah.
And one can argue, oh, but it can send information by, like if you increase the number of layers. And it's like, yeah, you want to know what also can do that? A convolution.
Yeah.
It increases the receptive field as you increase the number of layers. This is just a convolution, and that defeats the purpose of attention.
Does that even that convolution even work for transformers, like feeding that information to the next token?
Yeah, I mean this is sparse attention. This is what they do, and it is the same thing as a convolution.
Right. Yeah.
It's a convolution over time.
Makes sense.
It's the exact same thing. It just looks different.
But like mathematically, how is that like passing towards the next token though?
What do you mean?
Like because like the theory that this works is that let's say the previous context is encapsulated in token 3 and token 4, right?
Yeah,
So like
but it's not.
Oh, okay.
Because you still have token 1 and 2 that you're not attending to. So you don't have information from token 1 and 2.
Like at all, theoretically.
You do technically after some layers, like if I have, say, like if I have layer 1, then layer 1 is going to say, okay, token 3 is going to be token 1, like value 1 times some weight,
Yeah.
plus value 2, plus value 3. Then technically the output at time step 3 has information from 1 and 2. So in the second layer...
So you assign the O3 to like the new V3?
Yeah, the third output.
Yeah. Okay, got it.
So technically, after the first layer, this has information of 1, 2, and 3.
Oh, God.
But, like, so does a convolution.
Yeah.
Like, there's a reason you have this full attention matrix, and that's that every output can be, like, if you wanted, like, let's say we have this really, really small. Like, let's say we have a window size 3, and let's say we have a sequence of 512. The last token, I don't know how many layers you would need. You would need a ton of layers just to pass the first token to the last token.
Wow.
And that's the same thing you see with the convolution.
Yeah.
It increases your receptive field, but slowly. But also, that assumes that this token only needs to store information, but it also needs to make a prediction. So it has this task where it needs to store information for the future tokens, but it also needs to do a prediction itself. So it's like,
Right.
now it has two things it has to do, and it's like, it just doesn't work.
Like, what does that even mean? Like,
Well, it can either pass information so that future tokens can get it, or it can, so it can just accumulate information, but then it also needs to make a prediction for the next token. So you have two tasks that it needs to do now.
Okay.
And it's going to optimize for one of those, and that is making the next token prediction. So yeah, it's a stupid idea. Don't do sparse attention. So linear attention. I'm gonna erase this. Yeah, sparse attention makes sense. It's just a convolution. It's just like it's just selecting parts of your attention matrix. That's all it's doing.
It's really interesting. I didn't know that.
Yeah, it's
I think mathematically it'd be identical.
it's identical to a convolution. It is a
It
convolution.
defines a convolution.
Yeah, it literally is a convolution.
Yeah, I didn't think about it like that.
Yeah.
Like I knew long former is like sliding window, which sounds pretty stupid.
That'll be a theme you see in current attention or in current papers. They're like, what if you take this attention matrix and you... Let me give you an example. Let me give you an example of something. So you see this formula here. Wow, really good formula. Now let me say I have... wait, why is this an A? That should be an O. There. O is equal to, let me change some things. So I'm going to say we have the softmax of query key transpose times our values, our normal attention. Now what I'm going to do is I'm going to say, like, these are time dependent. Like these query key and value, we all know you apply a projection matrix, right?
Okay.
So now what if I say, actually let me add the shapes. This is S by D, this is going to be D by M, and this is going to be M by D. So now let me say I'm going to make K and V. I'm going to make these learnable matrices, and that's it. So K is going to be a weight matrix in R D by M, and V is going to be in M by D. Now, if you look at this formula, tell me what it looks like. Because it should look pretty familiar. Let me change it
It's a
to that.
two-layer
Exactly.
feed-forward network.
And people call this, what do they call this? They call this something stupid. They call this an attention mechanism. This is a two-layer feed-forward network. Let me replace
So
this.
it's conditioned on the query and nothing else?
No, it's just a two-layer feed-forward network.
No, but I'm saying like, so it's, the only thing that it's conditioned on is the query, and then it's just an MLP after that.
No, it is just an MLP.
Mm-hmm.
It is nothing. It is just an MLP.
Is
What
WX
is the endpoint?
Yeah,
Yeah, you just replace that with an X, and
exactly.
it's just a,
It's an MLP, but with softmax. And softmax is a worse activation function than Silu. So it is a stupid MLP, and this is what researchers are like, oh, well, what if we do this? And it's like, oh, it's a new attention mechanism. It's like, no, it's not. It's not a new attention mechanism. It's
Like,
an
when
MLP.
when did that come about? Like, recently? Or-
Yeah, there was a paper I read like a month ago or something, and they proposed this as a new idea, and they're like, it's better than an MLP. And I'm like,
It is not MLP.
it's actually worse because softmax is a worse activation function. So I don't know how you're getting better scores because this is an MLP. So it's stupid. It's like, what? Like, I don't trust any
hey,
results.
but that's what programmers do. Mathematician would never do that.
It's so,
We do that. Like, that's where the innovation comes from.
yeah, we actually do a rename where we're like, nah, forget this. We're not making this W1 and W2. We're not making this WU and WD. We're making this K and V, and we're also renaming this to Q.
No, but there's gotta be something else.
No,
to
this is it. This is the whole thing. This is
In the instantiation of K and V,
no, it's the same thing.
there's no.
Yeah. And there were two papers that came out around the same time with this idea from Meta and Google.
No way.
Yes, and Meta and Google. And people are eating this up. People are like, oh, this is such a good idea. I'm like, what are y'all
The only
talking about?
difference would be that compared to a traditional MLP, in this case, Q is still linearly projected, right?
But no. I guess there's another projection, but a projection and another projection is one projection. It's a linear
One bigger
projection.
projection.
Yeah. Like if you have X and you have W1 and you have K, then I can define W2 equal to W1 and K. So it's
Yeah.
one projection, it's the same thing. The only difference is softmax activation function, which is worse for an MLP.
That's interesting.
So it's-
Sorry, can you define projection?
Just a linear
yeah,
layer.
yeah, just a linear layer.
Not really.
So like if I have X and I have W, where this is like of shape D and this is of shape D by big D,
Yeah.
and that's just projection.
Because then you'll just get a.
Well, I'm just call it like this is you can call this a projection.
Okay, you'll just get a 1 by big D.
Well, I'm technically projecting it into I'll name this E. I'm projecting a vector of size D into this RE space.
Yeah, that makes sense. Okay. Yeah.
And you're attaching a bunch of learnable parameters to X.
Yeah.
While you're at it.
Yeah, that's your way.
Yeah.
So stupid things that you'll see. So if you see anything weird happening with and you can also make this Mo. You can turn this into Mo.
What's Mo?
You don't know Mixture of Experts? Oh man. So basically, what you
I've heard that before.
yeah.
I've seen that in papers. I thought it was just like some bullshit.
It is good. You can turn this into so it's good if you want to train on a ton of GPUs and you want to push parameters into your model. I could talk about Mo real quick. So basically, you have the two parts. You have your attention mechanism and you have your feed forward layer. And the idea behind Mo is we can do a feed forward layer, but we can have multiple feed forward layers where one, like, we have a token, right? And that token is sent through a feed forward layer. The idea is we have multiple feed forward layers, like we have feed forward layer 1 and 2 and say 3. And each of these will specialize in it. So this will be like, oh, we send it to this one.
That's what it is.
There's more to it. It's actually a clever idea if you want to scale up models. It's both a good and it's like, it's fine. Like it's good if you want to scale your model up. I'll talk about this. But basically, you just add it here. So.
Oh.
Well, that's called an ensemble.
Yeah, it's basically an ensemble method, and this is easy. Like this is trivial. What you do is you say, well, we're gonna add sparsity. Do all y'all know? Do you know Mo?
No.
Oh, cool. Yeah, then I'll totally go over this.
Oh, yeah, that's awesome.
Yeah.
That
So
sounds like something like a programmer would come up with.
yeah, this is a total programmer thing.
I like it.
So no, it's you will see this in every big model. Every single big model has this.
Isn't it like in the transformer paper?
No, it's not.
Oh.
No, this is recent thing, like 1 or 2 years ago.
Okay, never mind.
So actually, let me do this. So we have this expert. We have this set of experts, and we have this token. So like you have S tokens, and you send it through the feed forward layer. It's independent of time. So we're just going to look at one token because you apply it to every token. So given a token, what we want to do is we want to sparsely send it to some of the experts. So we want to say, oh, this expert, or intuitively, you can say have 100 experts, and one expert's like, oh, I'm really good at recognizing the sentiment of something, or I'm really good at, I don't know, something intuitively. What actually happens is not really interpretable, but that's kind of the intuition behind it. So let's just say we wanted to send it to 1. So we can have a vector, and we can have some router. So we'll call this router R. So we send this vector to this router, and this router will say, I think you should go to this feed forward layer. So then it'll output this feed forward layer is just normal feed forward layer. It'll do its computation, and it'll output something, and then you accumulate all the outputs. So we can send it to, say, the top 2. So you basically have this top case selection. That's how we send it to this one, and we just accumulate the outputs. So how do you route this? You route this using a MLP. So let me define the actual shapes here. Let me just say the feed forward layers are a matrix multiplication. Or, I'll say they're feed forward layers. So let's say, these are feed forward layers where you have your up projection here and your down projection. That was a terrible drawing, but your normal feed forward layer. So every expert is a normal feed forward layer. Don't worry about how many parameters that takes up. You can define your expert to be whatever you want. The main idea behind an expert is the input is of shape D. You throw this through some transformation, so usually an up and down projection, and then the output is also of shape D. So just an expert is some transformation. So what we need to do is we need to have a router. So our router is going to be defined as a weight matrix, which is in our D by the number of experts. So what this is going to do is it's going to take our vector of size D, and it's going to up project it to the number of experts here. So let's say we have 10 experts, or let's say we have 1,000 experts, and let's say this is like, 16. So this is 1,000, then it'll up project this to 1,000 experts. Then what we do is we apply softmax to it, and we take the top scores. So that tells you where your experts should go, or where your what expert the token should go. So let's say it picks like this one and this one or something like that. Then you get the indices and you send it to that. So here it would...
Wait, explain that again? Sorry.
Oh, so you basically want your router to say where this token is going to go. Mm-hmm. So you take your token of shape D and you up project it or down project it to the number of experts you have. Mm-hmm. So this is your weight matrix here of shape D by a number of experts, just a linear transformation. And then you apply softmax to it or you don't need to apply softmax, but if you want to make it a distribution, to say, basically give me a score for every expert, and you take the top 2 to send to those, or top K to top K selection, and you send it to those top K experts.
D is just one token?
Sorry. D is equal to 16. There we go.
Okay.
This is x at time t. So this is one token because you're applying this transformation to every token.
Right.
And the idea is every token will get its own set of experts that it will be sent to.
Oh.
So you have like a set of 1,000 experts.
Right.
And the first token may be sent to the 50th and the,
Yeah.
101th.
Okay.
And the second token will be sent to some other ones.
That's really clever. If you have like a stable router.
Yeah. And so that's a good point. I'll get to that in a second. So yeah, that's the stable part is a good point. So there's a problem here. So I'm just going to define this here. So let's say our output at time t is equal to the sum. I'll define it over all the experts. I is equal to 0 to the number of experts, so I'll call that E, of our weight. Or actually, it's just the output of the experts, so number of experts, call it, sure, that works, of expert of I. So this is what experts are we sending it to? So this is just summing the expert of xt, expert I of xt, there. So basically this is saying we just sum the outputs of all the experts. There's a problem here. And the problem is the router is not learnable because there's no gradient flow to it. So how do we make the router learnable? There's a very clever trick, and it's called multiplying. Basically what they do is they say, all right, so we have this weight here, and this weight is given to every expert. So what we're going to do is we're just going to multiply this by the weight here. What do I call that? I'll call this R. So our router of xt. So this will give us so this here, x is going to be our input. We send the input to our router. Our router then gives us a weight, and we multiply the expert output by that weight. So we have gradient flow. If you think about it a little bit, it does make sense, because if an expert should be used more, it'll have a higher gradient. Like if the expert is important versus if it's not important, then the gradient will be lower, so it'll minimize it. So it's like, I can kind of see, like, sure, it's kind of a trivial idea, but it does make some sense. So this is essentially what you have. And you can sum over all the experts if you define R as 0 if it's not selected, and 1 if and the weight if it is selected. So there is a problem, and that is, what if we have experts that aren't used, or what if we have there's some problems with like experts, and like what if you have an expert that's not used? Getting email. There. Yeah, what if you have experts that like aren't used? Like that's useless computation. There's like expert balancing that you can do. So you can define a loss that says an expert should be, this is an active problem right now. How do you get experts to actually be used? So you can define a loss that says like an expert that is used so much should, like, you penalize the model for using an expert too much, but what that'll do is that'll smooth out the expert probabilities so they become close to uniform. What DeepSeek did is they said, like, instead of doing a softmax where we have relative scores, we're going to do a sigmoid. So the sigmoid basically just says, it's just like you basically have a sigmoid for every expert, so it's not relative anymore. But the reason you can do that is you can add a value to the sigmoid. So like, let's say this gives you a value of like 0.9, and this gives you a value of like 0.1, and this gives you a value of like 0.5 or something like that. So we have 3 other experts or something like that. What they did is they said an expert that is used, and then they add like S1, S2, and S3, I think. It's something like this. Yeah, I'll define S. So S is some score that you're adding to it, so some bias. And they define a bias as if a expert is being used a lot, the bias will be low. And if the expert is being used a little bit, the bias will be higher. And they define a heuristic to work with that. And in this way, the model isn't forced. Like it's kind of forced to use some experts more than others, but it's better than applying a loss. But they also apply the loss at a very small scale in case there are some weird outliers. And this works better. It adds, it makes some experts actually used more than others. So you want expertise more than others, but you don't want it to be to the extreme where your experts aren't being used at all and where one expert's being used. So this is an active area. Like, how do you balance your like active research area? How do you balance the experts? Because you can either have no balancing where one expert will probably be used a ton, or you can have all balancing where it becomes uniform because you apply a loss or something. So yeah, trade-off. The reason you can parallelize this is, what if I have this on GPU 1, this on GPU 2, and this on GPU 3?
Huh.
So then all you have to do is you have to send the tokens to their GPUs, and yeah, it works pretty well. And then you just do an accumulation here.
And it works objectively better than just having a giant feed-forward layer?
So it works, so yeah, it's because you want to shard it. Like, let's say I didn't have the memory to store a giant feed-forward layer, but on one GPU. But if I have 3 GPUs, I will have enough because it's just one feed-forward layer. So it is, if you can store it all in one feed-forward layer, it is not better. But you usually can't, and they usually have like 1,000 experts. Like, you can't store that in one feed-forward layer, but you distribute it across a bunch of GPUs. And this is why you see in like DeepSeek where they say they have 600 million billion parameters, but the active count is like 16 billion. And that's because the selected experts, like, you technically have 1,000 experts, and technically that's 100 billion parameters, but the active count is the number of experts used at a time. So if I have one token, it's being sent to, say, 1 or 2 experts at a time. So the active parameters is very low.
Oh, so like once it's trained,
That's
you
yeah.
can optimize a lot better.
Well,
Is that what that is?
there's two parts to it. It's once it's trained, it's awesome because you only have a limited number of active parameters being used. So
Yeah.
the amount being used is a lot less than the amount being than the number of parameters. So technically, this means the model is of size 600 billion, but it's a 600 billion parameter model, which is way better than a 16 billion parameter model, but it only uses 16 billion parameters. So you get the scale without having to actually use the scale. But it also works during training because, like, if you have 1,000 experts, you can't store that on one GPU. You need to store that across multiple GPUs. And
But during training, that's just distributed computing with a few optimization tricks, no?
so there's different ways you can distribute, like you can do distributive computing. This is a smart way of doing it because the alternative is I have one feed forward layer,
That just gets partitioned.
yeah, which is
Yeah.
very bad because it is so slow. Like, if you chunk a feed forward layer, every token has to, like, if we look at a feed forward layer versus, let's define a expert as a single projection. Like, if we define a feed forward layer here, we'll define a massive feed forward layer. So this will be of shape D by, I don't know, big D or something. Let's define an expert as one of these projections here. So D will be equal to the number of experts. So simplifying this a little bit. Then in the normal case, you would have to send a token through every single one of these functions. So let's just define one expert function as one of these rows. So you have to throw it through every single one of these, which is expensive if you have like D is equal to 1,000 or something like that, or D is equal to like 1,000,000 if you have 1,000,000 small experts. So you have 1,000,000 functions in your feed-forward layer. So just a normal feed-forward layer. But for mixture of experts, you're only sending it through a subset. So you're only sending it through a few of these, which makes it it's more sparse. So since you're using, and the reason it's worse is because you're not doing a dense computation. So it's worse if you had all the parameters used at the same time, but you can't use all the parameters at the same time because you don't have the compute for that. And if you were to shard this, you would basically say like this half or this half is going to be on GPU 1, and this is going to be on GPU 2. So this is bad because you take the outputs of this, which every token has to go through. So every token is sent through this here, and every token is sent through this here, and then you have to do a sum, and that's expensive because you have to send all the tokens to both GPUs, and then you have to send all the tokens back. In Mixture of Experts, you only send some tokens to GPU 1, some tokens to GPU 2, and you collect them all. So it's a lot more efficient.
So Wait, but how does this model train how does this model work in inference? Like, do you still have that router weight and then?
So you can make some optimization. Yeah, you have the router weight.
Oh, you still okay?
You do this exact same formula up here,
Right.
but instead of sending it, like, you only send the token to where it needs to go.
Right.
So let's say I have like 8 GPUs and I have like one GPU that happens to have all the experts I need.
Sure.
Then I would only send it to that one GPU and then I would send it back.
Okay.
So you're only using one GPU. Or during inference, let's say I have everything on the CPU, then I only load the experts on the GPU that I need.
Huh.
So the memory is a lot less.
What if you partition the feed-forward layer vertically?
That's another way you could do it, but I mean, it's the same problem.
Would that fuck with the gradient flow?
No, well, it would. It depends on how, like, I mean, it's a good point because you basically have to take the input gradient, so the gradient from the past layers, and you have to distribute it to both. Because your gradient is defined, like if we have O is equal to XW, then your gradient DL over DO, or DL over DW, is equal to, I think it is DL over DW X transpose. And you have to send this to both, and this is a very big matrix that you have to send to both. But for a mixture of experts, you only have to send like a part of this.
Yeah, I don't really.
It gets really annoying with
It's really
gradients.
clever.
Yeah, it's a clever idea. It's what you see. Like if you want to make a big model, you use Mo. You don't use a normal feed-forward layer. So this is a drop-in replacement for your normal feed-forward layer. Worst case scenario, it uses one expert, and that's the same as a feed-forward layer.
Right. That makes sense.
So yeah.
Does the in train time, does every single feed forward gets trained?
It depends.
Like, every expert gets trained.
So it depends on how you train it. You can do this as a dense computation where you send every expert to every feed-forward layer.
Okay.
And the output is either 0 or the weight. If it's selected, it's
Right.
the weight, and it's 0 if not, which is stupid. You could do that. It's easy, but it doesn't utilize the sparsity. What you usually do is you usually send the tokens and accumulate them, and you either have a 0 or you just treat it like a normal gradient PyTorch flow. So during training, you basically want to subset your token, send it to one of the experts, and it does its stuff. I don't really want to get into the GPU things because it's ugly, but you basically have to send it to the GPU, and the GPU is sitting there waiting, and it's like, oh, I got these tokens, and then I send it through, and then you have to send it back. It's a mess. It is a mess. During training, it's just like normal training. You can think of it that way.
Okay.
Like, don't think of it as anything special. It's just, how do you send it to the GPU and how do you receive it? That's the annoying part.
Okay.
But yeah. So that makes sense though? Like Mo and why you would use it.
I never even knew about it.
Yeah. Yeah, no, this is where you hear the active parameters versus the total parameter count. It's because the active parameters are the experts you use. But there are problems with it, like it's sparse, so it's not going to be as good as a dense model.
How
So
did we get here? Did we what happened? Like, does this relate back to linear attention somehow?
oh yeah, how did we get here? We didn't even talk about linear attention yet.
Yeah, no.
No, this is a really important thing because you see this in every model. Oh yeah, I was calling this stupid. The attention mechanism whenever you replace the keys and values, and I said, oh, it's like Mo, and then somebody
Yeah,
asked, what's Mo? There we go.
No, that was me.
Yeah. All right, let's talk about linear attention. The main thing. No, I think it's good that we talked about Mo because Mo is pretty important. Like you see it in every model.
And like you said, it is active.
Yeah.
It's an active area of research, so.
Oh, it is. Yeah.
I guess that's a good reason to.
It's if you want to make a big model, you use that. It's basically like forcing more parameters into the model without having to compute those parameters.
Right.
All right, let's talk about this. So how do we do linear attention? What you do is you remove the nonlinearity. So this is S by D, this is D by S, and this is S by D.
Yeah.
So this is quadratic because you have this part here. That's why it's quadratic. You have to do this. If you try hard enough, actually, you can't. You just can't get around computing the softmax. There is flash attention, but in the end, it does do the squared computations. It just does it in a smart way. So let's remove softmax. Let's go. All right, we're done. Linear attention. No, I'm kidding. So if you remove softmax, you can do a right multiplication and then a left multiplication. So let's, usually you have your parentheses around here, so you have to do S first, inner product on D. But instead, we can move the parentheses to be around K and V and do an inner product on S. And if you do this, you have a D by D matrix that you're storing. So this is quadratic in terms of the dimension. And note that this is the head dimension, so head dimensions are like 16 or something. They're really, really small.
Oh, D is smaller.
Yeah, D is
D is my input, right?
D is of size 64 or something like that, because it's the head dimension.
Okay.
And S it can be 1,000,000.
Whoa.
We'll just call it 1,000. So S is your sequence dimension.
Sure.
So, if you're using Gemini, they have 1,000 or 1,000,000 or something like that. So this can be 1,000,000 and this can be 64. So if you choose to do this right multiplication, you have an inner product on S rather than D, and you have a quadratic, it's quadratic in terms of the dimension. And then you multiply by this here. So it's just an inner product on this D, and you have your output.
So you're gonna S by D.
Yeah. So it's the exact same computation except you remove the softmax.
Yeah, because matrix multiplication is, what's the term?
Well, it's not associative.
It's not associative?
It's commutative? Is that the
No.
What's the property?
It's associative but not commutative.
Oh, okay. I had it the wrong way around.
It has to be abelian to be commutative.
All right, so it's associative, not.
Commutative.
Yeah. I always get those two mixed up. Yeah, so you can move the parentheses around K transpose V instead of Q K transpose, and
Okay, yeah, it's associative. Got it.
yeah.
Sorry, I'm looking up what associative is.
Yeah, I forget those two. So yeah, that's the basis for it. So there are problems with this, and that is that there is no nonlinearity, so it's not that expressive. What the first idea is we can approximate softmax, which is a stupid idea, and
Like a polynomial approximation.
one of them was. But it all boils down to what we can try to approximate this inner product on the dimension by some kernel function. So we'll define this as some kernel function of Q and K transpose and V. So it gets into kernel functions, and then you end up with stupid kernel functions like, oh, what if we use a Gaussian kernel? And it's like, what are we doing here? But you can split this using the kernel trick,
Yeah.
and you get this here. Basically, I don't care what you define your kernel as, it's just a function on Q and it's a function on K.
Uh-huh.
And what I can do is I can define Q tilde as the function of Q, and I can define K tilde as the function of K. So in the end, this becomes Q tilde K tilde transpose times V. I don't care what function you're applying to this, it's this. This is the formula you have. So yeah, it all boils down to this multiplication here. So there are some problems with this. And I'll describe a few directions you can go with this, and some problems. So, one problem is you don't have this nonlinearity, so it's not as expressive, and it's not a vector. It's not a vector that you're applying this nonlinearity to. A second one is the mask. I'll talk about the mask in a second, and then a third one is you actually run into some magnitude issues. It's not stable.
Question on the math.
Yeah.
Why is this linear?
Oh, it's linear in terms of the sequence length, because if we do multiplication of Q and K transpose,
Right.
you have an inner product on D, so you have an S by S matrix.
Right.
But if you do it on K transpose V first, then you have a D squared. So it's linear in terms of the sequence length. Like the complexity, if you do left multiplication and then right, is S squared D. And the complexity, if you do
Is SD
right,
squared?
yeah, SD squared. And it's squared in terms of the dimension, so it's much better.
We just call that linear because it's fun, or
Well, it's linear in terms of the sequence length, which is what
Still-
matters.
still would be a
Oh,
huge
okay.
difference.
right?
Because
Okay.
S would be much bigger.
Yeah, S is way bigger than D.
So we're just basically treating D as a freaking like constant, whatever.
Well, D is a constant.
Oh,
Yeah,
oh.
we're not treating it like constant. It is constant.
Okay, that's why. All right,
That's the
got it.
feature size.
Yeah.
That's the
Yeah,
feature
yeah,
dimension.
Yeah, S is your sequence dimension, and D is your feature dimension.
Yeah. Okay. Yeah. My bad. Yeah. Okay.
Yeah.
That makes sense.
That makes sense.
Sorry. Yeah.
Yeah.
Somehow I thought D was another variable.
No. D isn't a
Yeah,
variable.
no.
You're not alone. I'm not really understanding this either.
What? What's wrong with it?
Like like, is the phi supposed to, like,
That is
act
some
as a
function.
nonlinearity?
So the idea is you can so the first idea is we can take softmax and we can approximate it using a kernel.
Mhm.
And the kernel uses a kernel function specifically, so you can decouple the query and the key nonlinearity.
So that's what it's doing.
That's the idea.
So you're applying a version of nonlinearity to both Q and key separately?
Yeah, and the idea is the combination of those two will form
Resemble a softmax
Yeah.
via some sort of a kernel trick.
right. And
That's so clever.
it's
Yeah.
not though.
It's not.
So, and that's why I define it like this, because I can throw any nonlinearity I want on Q and K. In the end, well, it's clever and it's not clever. Like it's clever, but not in the way that it was first described as a kernel trick. Like you can describe it as a kernel trick, but in the end, it is still just a query and a key matrix that end up having an inner product. So let me draw it out.
So you're saying I will win Nobel Prize if I can find a kernel trick that exactly like mathematically simulates softmax.
I have a claim that I will make, and I have a claim that I'll talk about, and my claim is you can either have softmax or you can have linear attention, and there is no equivalency. It is
You wanna
impossible.
Prove that.
I can't prove it, but but my claim is you can either have softmax quadratic attention,
Yeah.
which is expressive, and I'll talk about why that's expressive
Okay.
to some extent, or you can have linear attention, which is less expressive, but the two are completely different. You cannot define an equivalency between those two, because if you define a like softmax has to be like you can't decouple softmax. It just doesn't work. My claim is that you cannot find a function that you cannot find two functions where the inner product is equal to something as expressive as softmax. Because if you do, I can define my queries and my keys as whatever function you define and write it like this. And if I write it like this, it's not quadratic, it's
Yeah.
linear.
Yeah,
So
makes
no
sense.
matter what two functions you give me, I can define it like this,
That makes sense. Yeah.
which can never be written, which
Because
is
it's
linear.
not
Yeah.
quadratic. It's just not.
Like I can make it quadratic, but I can also make it linear.
Oh,
But
okay.
for softmax extension, you can't make it linear. You can't make it linear, so it's
Right.
impossible.
Okay.
That's my claim. I haven't proved it.
Also, that operation over there, where you separate phi q and phi kt, that's also linear.
Yeah,
That's also a linear operation.
yeah. So my claim is that you can't like they're completely different and they have cool properties. So yeah, let me just talk about like what this looks like. So if we have our softmax function, well, let me define like phi first. So phi is usually like phi of x is like initially it was like 1 plus elu of x or something like that. Basically, you can define this as like a ReLU of x.
Right. Yeah.
And
Everything's really.
yeah, so this runs into problems. Everything is ReLU. Yeah, so this runs into some problems, and I'll write this out. So if we have our matrix here, yeah, and I'm not going to talk about causal right now. I'm going to talk about bidirectional because it's easier. But if you make causal, you run into problems, and I'll talk about that. But it's annoying whenever you make a causal. So we're going to talk about bidirectional, and basically what we have is we can look at this inner product matrix, so the quadratic matrix that you see, because it's easy to visualize that, and I'll show you one of the biggest problems. So if we have softmax, then O at time t is equal to the sum as I ranges from 1 to 0 to s of e q, this will be O at time t, q at time t, I'll make this little s is equal to 0 to m. So m is going to be our sequence length, s is just indexing the sequence length, t is going to be our output token, so some token at time t. So this is q at time t. Q basically says what your output is going to be. This is ks and this is vs over the sum s equals 0, m, e, q, k, or q and s. So this is just softmax attention right here. If you remove it, then you basically get, so this is softmax nonlinearity applied to one row, and you're summing along that row. That's all I'm doing here. And you get one output token. That's all I'm doing, nothing special. Now if we change this to linear attention, then you basically have, you have q tilde and k tilde, but I'm not going to write q tilde and k tilde anymore. I'm just going to write q and k, because it's the same thing, essentially. So this is q, vs, and ks. So this runs into a problem because there's no normalization. If you were to just do this operation and you were to increase s, let's say this has a defined interval that the values are contained in. So like basically at any output, as I increase s, it increases the, like let's say every multiplication I have has some interval that the values are in. Like it's in the range negative infinity to infinity. But let's say the interval that let's say for some reason we contain these values in some way so that we have some nice property. Like you can do that, I'll show in a second. But let's say this inner product at every time step s, has a value that ranges from -1 to 1. Let's say I have that. So that means for every s, that means for every token I have, the possible magnitude of the vector increases by a unit every time. And you can see why this would be a problem, because if I have, as I increase my sequence length, the magnitude of the output grows linearly or exponentially, depending on, or it grows linearly in terms of this unit interval. So that means, like, softmax doesn't have this problem because it normalizes by the weights here. But linear attention has this problem because you don't have a normalization factor. So what can you do? Like basically, as I grow my sequence length, it just keeps increasing the magnitude of the vector, the possible magnitude of the vector. So we need to normalize this somehow. There's two ways you can do this. You can either do this using this up here, or you can do this by defining a denominator. So I'll just use this up here for now. So basically what we're going to do is we're going to add a denominator that normalizes by the weights. And the weights will be the inner product of the queries and the keys. So this will be s is equal to 0, m, and we're basically going to take softmax, remove the exponential, and it is still linear. So we have qt, ks, vs over the sum s equals 0 to m of qt, ks. And you can define, like, you can basically decouple the sum, the numerator and the denominator, and it's still linear. I'm not going to, I could show you. You can basically move q out, and it's still linear.
Yeah.
So this is what you see. So like in most of the recent papers, if you see a linear attention mechanism, it's usually this here.
So this is like linear, normalized.
Yeah, normalized linear attention, because it needs to be normalized. Otherwise, as your sequence length grows, the output grows linearly.
Right.
The
so
magnitude.
Like,
Yeah.
Okay, yeah.
Because there's nothing to stop it from growing.
Exactly.
So this is one way to normalize it. What I did in my paper is I said, what if we have, what if we make this cosine similarity? So then the magnitude is contained between the interval -1 and 1. And what you can do is, like, if we have the inner product of q and k, so actually I'll define it. So this is one way of doing it, but this is inefficient. This is somewhat inefficient. You can also do the, like if we define the inner product of q and k, so q k transpose is equal to, like if we define this as cosine similarity instead of softmax, you can decouple that. So this is q over the magnitude of q. at time t multiplied by ks over ks. So you normalize q, you normalize k, you do the inner product, and the values are now contained between -1 and 1. And if you do this, that means that you can divide the sum by the magnitude, and the output vector is going to be of value 1. So another way you can do this is you can say O at time t is going to be 1 over the sequence length times the sum from s equal to 0 to m of this here. So this will be qt over the magnitude of qt times ks over the magnitude of ks times vs. There. So two different versions you have. This one here, since it's contained in the interval -1 and 1, you can just divide by m. This one here, you divide by the sum of the weights. So those are the two ways you can normalize it. That makes sense?
Yeah, that's fine.
So
I
you
don't know
can
if that's cosine similarity though. I don't know if that term is correct.
No, it is. You do the, so it's the inner product on the q and k vectors.
Yeah.
So, let me write it out this way. So this is equal to the inner product of qk multiplied by qt times ks. There you go. So this is what you normally
Which is the
see.
angle.
Yeah. Which is cosine, it's the cosine similarity formula. But you can decouple it so that you normalize q and normalize k, and then you do the inner product. So you have this over here, which is decoupled, and that goes back to this formula up here. So phi in our case is equal to, like phi of x is equal to x over the norm of x. While in other cases,
You're right.
yeah. So this is one.
That does define the angle.
So, but it removes the magnitude information. So that's one thing you're missing out. In the case of ReLU, you still have the magnitude and angle information. Like if you define phi as ReLU, so basically phi is on here, phi is on here, phi is on here, phi is on here. Then you define, like if you apply it to there, you still kind of have the magnitude and you kind of have the angle, but now you don't have negatives. So with cosine similarity, you have negatives, which is the exponential also has negatives encoded inside it. It's just exponentiated, but technically it's still there. ReLU removes the negative information. This removes the magnitude information. So
Makes sense.
that's something interesting.
So it's just a cosine similarity times like the.
Yeah, so basically like your weights are the cosine similarity. So now for the interesting part. I can define, so we have O, like I'm not going to worry about the normalization. Normalization is some term you're dividing by. So that can either be the sum of the weights or that can be just m. I actually define this as m to some learnable power, a, but besides the point. We'll keep it simple to the sum s equals 0 m q t k s vs. So what you can do is you can pull this term out here. So pull it out there because it's not dependent on the sum. And this is interesting because you get an R and N. So if we have this, let's define our shapes. This is S by D, or rather this is 1 by D because it's our single output token. This is D by S, this is S by D. And this is an R and N where the hidden state is of size D by D. So let me draw it out for you. You can see the R and N though, right? This is your R and N.
I forgot the function for R and N.
Well, R and N is general, but I'll show it. So basically you have your, yeah, so this is your R and N. Basically it's saying I'm going to take the sum of all the outer products of K and V, and I'm going to sum them together until I get to, and I'm going to sum them together. So over my entire sequence length, from here to here, I take the outer product of K and V, so K transpose V. I sum them all together, and I multiply that by, I do the inner product on Q. So you can either do,
And then the summation.
yeah. So this is your hidden state right here, which I'll draw in a second. And this is your, basically you have, this is your hidden state, and you have this as your, this is the way you're observing it using Q. So you can write this as an RNN. And the cool thing is you can actually write this as an RNN going over your entire sequence. So this is Q, this is K. You can write this as an RNN going over your entire sequence if you make it causal. So I won't make causal yet, actually. But yeah, so basically this is, you can make it an RNN.
Because causal, you're just going down anyway, right? Just to
Yeah.
the next.
And I'll show the the formulation for that. Yeah, so you just pull out Q, RNN. But it's an additive RNN, like I was saying. So basically you have your hidden state going over all the keys and the values here. And you just have this as getting the output at that time step. Yeah, so does that make sense so far using this bidirectional? You just remove the nonlinearity, you add some normalization, and you can make it an RNN. Yeah, didn't lose any. Cool. All right, so now I will make this causal. So this is super efficient to compute.
Wait, actually, one second. Why
Yeah.
is this bidirectional?
Oh, it's bidirectional because I don't have a mask there. It's just this. It's just 3 multiplications.
Oh,
Yeah.
right, because you're okay.
Yeah, I don't have the
because
causal
it's
mask.
Entire.
Well, I don't have the causal mask there anywhere. So yeah, this is trivial to compute.
Yeah.
You just do right product and then you multiply by Q. Easy to compute. This is easy to code. Now when I add the mask, it becomes a pain in the ass. Yeah, let me just add the mask. Oh yeah, no, there's one thing I want to show first. So before that, I want to show another stupid idea. So let me, so if we take the numerator of our softmax, we have the sum s from 0 to m of e, q, t, k, s, vs. So right, this is softmax numerator. The denominator is just the sum of these. Now, a stupid idea, which, I mean, it seems fine at first, but it's very stupid, is what if I approximate this by saying s is equal from 0 to m of e, q, t, e, k, s, vs.
What?
So the reason this is stupid is because so it looks fine, but it's actually really stupid because this exponential here is applied to the inner product, while this exponential is applied to the vectors themselves.
Yeah.
Another reason why I think it's impossible for you to define, like, this is linear, this is not linear.
Yeah, because that's e to the qt plus k.
Yeah, so if we look at this is e to I from I equals 0 to 1 of qti ksi. And this right here is e sum I, or this isn't a sum, this is the sum of I equals 0 to d of e to the qti e to the ksi. So we'll go ahead and write it like this, ksi. There you go. Completely different. One is a sum, one is on the inner product, so this is an inner product space, and one is the inner product of that function. It's just like, it looks the same. It looks fine, but it's completely different. So just another note I want to make, like.
So that's kind of that's what you're losing by using the linear extension, right?
Yeah, well, it's a function on the vectors
Yeah.
rather than a function on the inner product
Inner
space.
product, yeah.
So
Right,
you,
because you want to avoid the inner product.
yeah, because if you do it on the inner product space, then you can't decouple it.
Yeah.
It's impossible.
Exactly.
And if you can decouple it, then it's just a function on the vectors.
Yeah, exactly.
So that's another note I wanted to make. Let me erase this. All right, so now let's make this causal because bidirectional is only so useful. So causal is a pain in the ass. This is where a lot of annoyances happen. So we'll define this as q tilde, k tilde, times the mask. Get out of here. It's no longer linear. It's really annoying because this here is a S by S matrix and it's a Hadamard product that you have to do. So it's no longer linear. You can't make it linear, so don't worry. But it's annoying because you have this stupid mask that it's there and you can't trivially compute this in linear complexity because you have to compute all S squared. Like you could if the mask, like let's say our mask is not dependent on time. So let's just say our mask is equal to like let's say this is S by D matrix or S by S matrix. And let's just say like you mask out the last 2 columns here. So you're masking out these. Like this is fine. You can define a way to make this linear still. This is fine. But the problem is that it's a mask that looks like this.
Yeah.
So you have to do this computation here. It sucks. Yeah. So
It's really interesting.
so it's a pain. What this does is it makes it into an RNN over time. So let me define this, and then I'll show you how you can kind of get around this. You can kind of get around it, but first I have to define it as an RNN. So if we have
Okay. If you do that sequentially, like it looks like an RNN.
pretty much, yeah. So you're basically going to store the keys and the values,
Yeah.
and you're going to use the queries as your projection. So let me define the matrix again here. Queries, keys, and let's just look at the outputs at every time step. So the output at time step 1 is going to be equal to the sum, the sum from I is equal to 0 to whatever. I'll use Python bounds to 1. That should be s. S is equal to 0 to 1 of qt ksvs. So this is equal to qt, that'll be q1. This is t right here. Right, 1 here. q1 ksvs. So this is q1 ksvs. I'm not adding the transpose. You get the point. Yeah, don't worry about it. So O at time step 2 is equal to the sum, s from 0 to 2, of q2 ksvs, which is equal to q2 k1, I don't know how to s there, v1 plus q2 k1 k2 v2, which is equal to q2 of k1 v1 plus k2 v2. Let's do the same thing for the first one. Q1 of K1 V1. Let me do one more. O at time step 3 is going to be the sum S from 0 to 3 of Q3 KSVS, which is equal to Q3. I'll just skip over here. Y'all can see where this is going. Q3 of K1 V1 plus K2 V2 plus K3 V3. And you will see this is an RNN over time. So this is here, and this one is here. So RNN. So it's an RNN where h at time t is equal to h at time t minus 1, or that should be an s, s minus 1 plus k transpose s vs. And your output at time t is going to be equal to your queries at time t multiplied by your hidden states at time t, which is equal to queries at time t times, so this is equal to, your hidden state is just equal to this part right here, s from 0, I guess I'll define this as I from 0 to s of ks transpose vs, or that should be indexed by I. So that's just the sum here with the query moved outside, and then this is just going to be that. So it's going to be the sum I equals 0 to s of ks, ki vi. There you go. So it's just an RNN where you're adding the outer products together. So what this looks like again is you have your hidden state at time t, you have your input that you're adding to it. Oops, ran out of room. You come down here. So you have your inputs, which is your keys, your queries here, your keys. Actually, I'll define keys, values. This is value at time t, key at time t, and your queries at time t. So what you do is you do the outer product of your keys and your values first. That'll give you a matrix of shape d by d, so that's your outer product. You add this to the hidden state. Your hidden state is then updated to h at time t plus 1. So that's just how you update it. That's your update rule. And then you do an inner product of your queries and your hidden state to get your output projection. So inner product, I'm just making it look like that, whatever. And this will give you your output, so O at time t. where this is of shape D, this is of shape D, this is of shape D, this is of shape D by D. Your hidden state is also of shape D by D, so that's your outer product, and this is of shape D right here. So yeah, does that make sense? I mean, mathematically it looks fine, right? So yeah, not too bad. But this is nice because let's say I'm doing inference, you can just store this hidden state. So that means this is linear when training and constant when I do inference because it's just an RNN. You just store the hidden state.
Yeah, but I guess my question is like, that's literally just like an RNN.
Yeah, it is an RNN.
So where does that advantage come from? Because you said it's still better than.
The reason it's better than an RNN, that like an LSTM, is because it is so efficient. So you get the sequence-wise scan that you're doing that is really efficient because you just have to do 2 multiplications. While a normal RNN, you have to do a scan over your entire sequence. So if you can get the properties of an RNN, you basically get the best of both worlds. You get the speed of attention, which is these 2 multiplications you have to do, while you get the expressive power of an RNN, which is, or the nice properties of the RNN, which is this constant hidden state going over the entire sequence.
So does it come down to the way you pack the data at the start?
So no, this is like, what do you mean by that?
Like if you pack the data so that you have a Q, K, and V,
Yeah.
and then basically run an RNN over it, it's more efficient than.
Well, it's if I start adding gates. So if I add a gate, you can't do this here. You have to like I can do 2 multiplications and I compute this entire thing in linear time. But if I add a gate, then what I have to do is I have to iterate over the entire sequence. So once I add a gate, then you run into the scan problem. You have to scan through your entire sequence. And that's slow on a GPU.
Right.
So this gives you the best of both worlds is, yeah. But once you start adding gates, it becomes problematic. So you can either have something that's super simple, that's super efficient. So you have 3 things. You have softmax attention, which is quadratic, super expressive. I can actually show that basically for, I don't really have to show it, y'all can probably see it, but basically for softmax attention, you have an RNN for every token. You have a unique RNN going over your entire sequence for every token. For linear attention, you have one RNN going over your entire sequence. So you can see it's a lot less expressive, but because you have one RNN versus one unique RNN versus an RNN going over, or an RNN for every token. So you can either have something that's more expressive, that is super computationally inefficient, or like it uses a ton of resources, softmax attention, or you can have something that is computationally efficient, that or memory efficient, that is less expressive, or you can have an RNN which is the worst of both worlds, which is like it's slightly more expressive than linear attention RNN, but it is super expensive to compute. So you kind of get the worst of both worlds.
That is interesting.
But it works. So it runs into the problems you would expect it to run. So like if I were to give you softmax, like I said, is an RNN that can go over the entire sequence for every token. So let's say so this is the needle in the haystack problem. Let's say I had a sequence just a sequence. And I ask you, like it's a sequence and maybe Bob kills Joe and Bob kills Joe at 4 a.m. And I have a sequence I have this sequence that is a million characters long. And then at the end I ask, when did Bob kill Joe? Softmax can say, oh, it was at 4 because I can directly go and look that up.
Yeah, it's just attention just goes Bob and kills Joe, and that's
Yeah.
all 1 at the attention
Exactly.
spot. You'll just find that.
The output will just be, in some way, it'll say, oh, the output's some combination, but I can literally say, oh, I want the 4 a.m. token, and I can send that to the output.
Yeah.
Linear attention does not know that because it is causal. It has to iterate through the entire sequence, and then it says, when did Bob kill Joe? But it can't go and look it back up because it's an RNN, so somewhere in that hidden state it has to know that Bob killed Joe.
Oh, interesting.
So it is way less expressive. because it's an RNN.
Yeah.
Like, it has to know to store that fact
Can you
before.
scroll down a little bit?
Yeah.
I just want a reminder on
But it's way more.
It's way more efficient. So what the best thing to do is to have some softmax attention, but a lot of linear attention.
Interesting, like in a hierarchy.
Yeah.
Okay.
Like if I have one, but so it's good, but it runs into issues like that. Like, it has to know what facts to store. If you're doing fact retrieval, it's not going to be good. But if you're doing other things, it can be pretty good. But it has its trade-offs.
Sorry, can you scroll up? I wanted to see the math.
Yeah.
version, sorry. Yeah, because yeah.
But there are obvious trade-offs. So if you see a linear attention mechanism that says it does perfect in the needle in the haystack task, that is bullshit.
It's essentially creating like a compression of the past.
Yeah, and it has to look up
Yeah.
in that compression. While softmax does not. So the hidden state for softmax is equal to the concatenation of all your keys and your values.
Yeah.
So your hidden state is equal to S by D for softmax attention. It's
So
just
a
concatenation.
Yeah, it's like a fully connected graph.
For softmax?
Yes.
No, it's just
Just
concatenation. Well, yeah, actually, no, it is a fully connected graph. It's one token that's connected to every other token. Yeah.
Wait, wait.
While for linear attention, you don't have this because it's an RNN.
Honestly,
So
for something like forecasting, like for time series, I think
linear attention should be pretty good at that.
an RNN probably solved that problem.
Yeah.
I don't think like
You don't need
theoretically-
attention for that. Yeah.
But that's what everybody does. That's what's so interesting to me.
Well, you don't need it because if you just need to sum everything up into a hidden state, and then that can be used as your future. But if there isn't something new that I see in the future that makes me want to go look at the past again, not really, because that implies that there's a fact in the past that I didn't know to store. I don't really maybe it would be better, but I feel like it shouldn't be.
And also, a lot of tasks, like including forecasting, have like a periodicity to it.
Yeah.
To the point where beyond a certain point, it's just gibberish anyway.
So you wouldn't even need but this is a trade-off you have.
Yeah.
You can either use an RNN that's really efficient. Like, this is an efficient RNN that's created. It's people call it linear attention. It's an efficient RNN. That's what it is. Or you have softmax attention, which is an RNN for every token. But just know these are the two things you have. You can have both, but that means during inference you have to store these key values. So it's linear. Like, during inference, softmax is linear, and the linear attention is constant. But if you add one softmax, then now you have one layer that's no longer constant. So, I mean, this is an active area right now. Like, what's the best way to combine these?
Yeah, that's so interesting.
So I'm actually using linear attention for a diffusion model I'm making, and it's pretty damn good.
Wow.
And also the loss, it's really close. It's really, really close to softmax. Like, whenever I was first doing experiments with GPT and BERT, it was 1% accuracy off, which isn't that much compared to how much you save. And for GPT, it's almost if you squint, you can see the different, but it's very, very close, which is interesting. So it's not going to be good at fact retrieval, but for other things, it's pretty good.
But coming from that RNN motivation, you could probably prove where the asymptote is of
Yeah.
what you can represent, right?
You should be able to, because it can only store the D by D, it has a hidden state that's of size D by D. So yeah, I don't know. This is a new thing, and I won't get into it tonight because it's pretty late right now. But there are ways that people are trying to do this via some gradient method. You can update the hidden state using some gradient, and that's, if you're curious, that's called learning to learn at test time. That's the paper, and it's it's a cool idea, but I don't think. In the end, it's still a linear update that you're doing, and the update rule is just a learned thing. Real quick, how do you make this efficient? Basically, the idea is we have to iterate over this entire sequence. So there's two things you can do. You can either do a efficient multiplication so you have an efficient method that is memory inefficient, which is left product So normal softmax attention. So you do this entire product, and then you multiply by the values. So that's efficient because you can parallelize it on the GPU, but it's inefficient in memory. The alternative is you can iterate over your entire sequence, which is very efficient in memory, but very inefficient in time. So you have these two trade-offs. So the idea is, what if you do the best of both worlds? What if we iterate over the sequence? And I won't get into the math because it's ugly. But you can block this matrix. So what if we block it like this? Here.
Oh god.
Yeah, it starts to get ugly. So if you do this, you will see that this part here is causal. So you have to do this as an RNN.
Right.
So you can either do this as an RNN, or you can do this as so you have the two choices you can do. You can either do the inner product like softmax, or you can do the RNN. So every part on the diagonal is that. So I'm defining my block size as 2, but you usually define this as something like the square root of the number of threads on your kernel, on your GPU kernel. And you compute these using the inefficient inner product. You're using the GPU efficient inner product on softmax. And the reason you do that is because these are small, so it takes quadratic memory, but the quadratic memory is local. So if this is like 128, because you usually have like 1,000 threads, then, and the square root of 1024 is like 1,000, or 128, I think. Wait, sorry, no, 64. I think it's 64.
Wait, square root of who?
1024?
1024.
So 64?
66.
32,
No,
something like that.
32, right?
Yeah,
32.
32 maybe.
32?
Yeah.
Okay, 32. You would make this a 32 by 32 matrix because you want one thread to do each computation or something like that. You can optimize the size to your kernel size, so the size of the block. And this is this is small, so it's quadratic, but it's not really quadratic. The off diagonal ones, so these parts here are easy to do because you can do a right product. You can do the efficient bidirectional right product and then left product. So these are easy.
Oh, okay. So those are basically.
These are hard.
Right.
So what you do is you
Because
define.
that's masked.
Yeah.
So you have to put a masking.
So what you do is you define this blockwise relationship where you can define, like, you don't have to compute this because you can define an RNN basically going down the direct to off diagonal. I'm not going to write out the formulas. Just take my word for it because it gets ugly and it's not useful. Basically, you have two computations that you do for every, like you're basically iterating down your queries, and you do it blockwise. And for every block, you compute two things. You compute this here to get your outputs, and you sum that with your current hidden state. And the hidden state is updated with the final values in that row. So it would be like if our hidden state is, let's say it stores 1 and 2, then I would need to add 3 and 4 to it, right? So if I finish doing computation for row 1 and I go to row 2, then I have the keys and the values compressed into this hidden state for 1 and 2. For token 1 and token 2. Then what I can do is I can say, all right, so I have these values. I can do a query projection on those, and I can add them to the query projection of 3 and 4, and I can get my outputs for 3 and 4. And then I update the hidden state using this row here, which gives me the key value outer product for 3 and 4. So you do an update to get your next two outputs, and you do an update to update your hidden state with the next two inputs. But don't worry about it. Just know that you can make this a lot more efficient by basically having an RNN go down here and you block this together. So there is an efficient method. It's just ugly. Don't try to cut this. Yeah. So that's how you make that efficient. Hopefully that made somewhat sense. If I write out the math, I don't want to write out the math. Don't make me write out the math. Don't do it. But if you're curious, Mamba 2 does it, and there's basically there's something called lightning attention. I think it's lightning attention. which does this. I don't know why lightning. It's basically the flash attention version of linear attention for masked. Because if it's not masked, you don't have to do the annoying computation of iterating over everything. So yeah, I mean that's a lot on linear attention. Any questions about it at all?
What are some of the seminal papers, I guess, besides Mamba 2? Mamba 2,
So Mamba 2,
lightning attention.
yeah, Mamba 2 and lightning attention are the two I would go for. Mamba 2 basically, an SSM can be this. Any linear attention you see is this. This is every single linear attention thing out there because I generalized it like this. Every single linear attention mechanism.
Where phi is just any function.
Yeah, phi is any function you want to define. I guess this can be like some other. We'll call this. What do we want to call this? We'll call this. I won't call it theta. You can define it as some other function.
No, but I think it's really nice that you just basically introduce the most generalizable version.
Yeah.
So that you can just recognize the pattern when you're reading other papers.
So the two things: you either have softmax extension or you have this. So you don't have anything else. Or you have softmax extension, you have this, or you have an RNN, which is in between the two. Those are the three things you have. Yeah. So hopefully that. Yeah, I think it's cool because this is a really active area, and it's really cool to see what is going to happen going forward. Because linear attention, people are missing out. Like you should be using linear attention, you probably also want to be using a little bit of softmax attention. Like it's not a drop-in replacement. It is a replacement of sorts. It's like it has way different properties, and it does pretty well, but it's not a drop-in replacement.
Interesting. Okay.
So linear attention should be pretty good at like tasks like summarizing.
Oh yeah, it should be awesome.
Just anything but information retrieval.
Yeah.
Because like mathematically, it's all the same until it's like info retrieval.
Yeah, it should be it should be good it should be good at everything but information retrieval, because information retrieval assumes, unless you put the information retrieval task at the beginning.
Yeah.
Because then it knows what to look for.
Okay.
But if you put it at the end, then it doesn't know what to look for.
Okay, that's true. Yeah, because you're.
But if you ever see a needle in the haystack task and they use linear attention, and they say it's good, it's not. It's not. It just memorized things. It's just not good.
Do you think linear attention's memory is better than softmax?
No, because the hidden state for linear attention is a D by D matrix, so the hidden state for softmax is an S by D matrix.
Oh,
It's
right.
yeah. You can think of softmax as having a hidden state that stores every single key and every single value.
So not good role-playing agents, which makes it entirely obsolete nowadays.
If you had one softmax layer, then it would probably fix that. Because then
that's a really good explanation of what a transformer is. Is that it's an RNN that stores every single token in its hidden state, basically.
the way I like to think about it is it's an RNN going over every single row. So like linear attention I showed is going over the diagonal. No, I don't want Galaxy. Get the hell out of here.
But it is like RNN at its most like expressive, basically.
Yeah, like
theoretically most expressive RNN.
No, that's a good way of putting it. Yeah, you can't have a more expressive RNN than softmax. So like for softmax RNN, you basically have an RNN here, 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 here. And when I say an RNN, I mean a unique RNN. So like technically cosine or like whatever linear attention mechanism you want to use, it technically is an RNN over every part of your sequence, but it's not a unique RNN. You can reduce this down to one RNN going over your entire sequence. So I say unique RNN, so this is way more expressive. It's an RNN going over your entire sequence, which means it can look stuff up. So yeah, you have your super expressive RNN, which doesn't do any compression at all, versus your linear attention, which does do the like max compression you could possibly do. And an actual linear what an RNN does is it usually adds to a vector. So this is actually more expressive than an LSTM. I would somewhat, because it stores it in this outer product matrix, while an LSTM stores it in one single vector that's added. So the hidden state's a lot larger. It can store a lot more information.
Yeah, I never thought of a transformer as an RNN.
Yeah, no, it's basically an
Like,
RNN.
especially for decoders, right? It's like they're just going down the path.
Yeah, once you add the mask, it's an RNN. If you don't have the mask, it is an RNN. It's an RNN that goes over your entire sequence.
Like goes through the whole thing first,
Yeah.
right?
But I wouldn't really call it an RNN. Like it technically is an RNN, but at that point it's like like it is, but it's not. Like if you don't have the mask, then it's an RNN that goes over your entire sequence. It's like, oh, okay, well, that's just at that point it's just a matrix multiplication, and using the RNN formulation, like it doesn't add anything. It doesn't add any
Like
intuition.
mathematically, there's no difference besides just a
Yeah, there's-
matrix. Yeah.
There's just like a lot of relationship, I feel like. I think maybe part of that is because like the ML community, the way it was like founded is it lacks in like the mathematical sort of like rigorous mathematical, whatever
Yeah.
construction, I guess. So people just keep rediscovering shit.
No, literally, like people rediscovered an RNN, and it's like really. All right, I'm gonna